This is the homework help video for the extra free fall problems for RHS Physics. I'll go ahead and work through all 5 of these one by one. We'll take our time, and I should be able to solve all of these for you, I think, and hopefully this will help you with some free fall problems. So let's go ahead and start with number 1. We've got Heather riding the detonator at Worlds of Fun. If Heather free falls for 2.6 seconds, what will be her final velocity and how far will she fall? The first thing we need to do is write down what we know. We know 2.6 seconds, so delta t here equals 2.6 seconds. We also know her acceleration, which is 10 meters per second squared down. And we also know her initial velocity because she's falling. That means that her initial velocity is 0 meters per second. What we're looking for here is her final velocity, and we're also looking for the distance that she falls. So we're also looking for delta d. Okay, this is a two-part problem because there's 2 questions, so we'll actually have to use 2 equations here. I will start by searching for VF. So to find VF, we're going to use VF equals VI plus A delta t. If you look at that, we have VI, we have A, and we have delta t, and we're looking for VF. So this fits our scenario perfectly here. If we plug some things in here, we're going to have 0 plus 10 meters per second squared times 2.6 seconds equals VF. So 10 times 2.6, and our final velocity equals 26 meters per second. And that should be your answer for the first part there. 26 meters per second. You can see how our units cancel out there as well. We're taking seconds and seconds squared right there, so the squared leaves, and we're left with meters per second. For the second part of this, we'll use a different equation because now we're looking for delta d. And I'll go ahead and change colors for us here. We're looking for delta d, so we'll actually use the delta d equals VI delta t plus 1/2 A delta t squared. Most of you have gotten pretty good at this because VI here is 0. We can cross this whole piece off, which is really nice. It makes the problem quite a bit shorter. And we have everything else we need here. So we're going to look at delta d equals 1/2 times 10 meters per second squared times delta t, which is 2.6 seconds squared. I'll have to calculate this a little bit here as we go. 2.6 squared is 6.76, so we'll have 6.76 seconds squared there times 10 meters per second squared and 1/2 equals delta d. If we multiply all those together, we should get delta d equals 33.8 meters because our seconds squared and our seconds squared will cancel. So we should take 6.76 times 10 times 1/2, and that should give us 33.8 meters. With sig figs, that would actually be 34 meters, so I should write that. 34 meters is actually your final answer there. So 26 meters per second and 34 meters. Let's move on to number 2. Which is, I think, a 1-part problem, so that helps us out a little bit. We've got a kangaroo that's capable of jumping to a height, that's a delta d, of 2.62 meters. This is number 2. 2.62 meters, and we want to figure out the takeoff speed. So we know that the acceleration equals 10 meters per second squared down. And let's look at this kangaroo here. We're obviously going to have a kangaroo that jumps up and then comes back down. The easiest way to solve most of these problems is actually to look at the second half of the jump. So we would look at from here to here. And the reason for that is because at the peak, we can say that VI equals 0. So we're going to do that right now, and we're going to say that VI equals 0. The other nice thing about that is everything is going down. Acceleration is down and velocity is down, so that helps us. We're also looking for VF. We don't know that, and that's the takeoff speed, which should be the same here And here, our takeoff speed should be the same as our landing speed, so that also makes this problem nice. If we go ahead and look for an equation here, we're going to use the VF squared equals VI squared plus 2A delta D. Again, we have VI, we have A, and we have delta D, so this is our equation. We're looking for VF. VF squared, still, VI in this case is 0, so we can ignore that, equals 2 times 10 meters per second squared times delta D, which is 2.62 meters. If we multiply all those things together, we'll take 2 times 10 times 2.62, and we should get 52.4 meters squared per second squared. Now we'll take the square root, and we should get VF equals, whoops, calculator error, 7.24. And with sig figs, we should have 3, so it's 7.24 meters per second should be our answer there. So 7.24 meters per second is the speed that kangaroo needs to take off it with. It is also the speed that it would land with. So here and here, it would have a velocity of 7.24 meters per second. We'll go ahead and go to number 3. For number 3, we've got Michael Jordan, a vertical leap of 1.29 meters. This is a very similar problem. Delta D is 1.29 meters. He has and we want to know what his takeoff speed is and what his hang time is. For the takeoff speed, I'll let you look at the last video. It's going to be almost exactly the same. Remember that Jordan is going to jump up and he is also going to come down. So I think you can use the same equation, follow the same steps there. For the hang time, it's going to be a little bit different. We're still going to look, however, at the second half of this jump. We know that his acceleration is 10 meters per second squared down. We also know that his initial velocity in this second half of the jump is 0 because he starts at the top where he has no vertical velocity. And if we're looking for hang time, we're looking for delta T. The best equation for this is going to be delta D equals VI delta T plus 1/2 A delta T squared. We know that our VI is 0, so we can cross this off. We also know that our delta D is 1.29 meters equals 1/2 times 10 times delta T, which we don't know yet, squared. If we multiply some things together there, we're going to be left with 1.29 meters. Oops, sorry. 1.29 meters equals 5 meters per second squared times delta T squared. Now we'll divide by 5, which will leave us with 0.258 seconds squared equals delta T squared, and now we will square root. And that leaves us with 0.508 seconds equals delta T. Now you might be thinking, gee, that seems like a short hang time, and you're right, it is a short hang time. Because we only looked at the second half of the jump, we also only looked at the second half of the hang time. So to find his actual hang time, we need to multiply this number by 2. So we'll take 0.508 times 2, and when we do that, we should get, and this is, I did this on the calculator with the answer, his total hang time, we'll say delta T total here, equals 1.02 seconds. And we should have 3 sig figs there. So 1.02 seconds is Jordan's hang time. And again, the first part of that problem is takeoff speed, and I'm going to let you solve for that because I think you can handle it. Let's move on to number 4. And I am running out of space, so I'm going to go back up to the top. On number 4, we've got a baseball popped straight up in the air, and it has a hang time of 6.25 seconds. So we've got a delta T of 6.25 seconds. We want to determine the height to which the baseball rises before it reaches its peak. So again, we've got this sort of a scenario. We know that the total time is 6.25 seconds. And again, we're going to want to look at half of this trip here. Again, it's easiest to look at the second half because everything is going in the same direction, and we can say that VI equals 0. We can also say that acceleration is 10 meters per second squared. And we want to know the height to which the ball rises. So we want to know delta D. Your equation here for number 4 is going to be the delta D equation. Delta D equals VI delta T plus 1/2 A delta T squared. We don't know delta D, obviously. VI is 0, so again, we can cross that off, which is great. And we're going to be left with 1/2 times 10 meters per second squared times delta T, which is 6.25 weight. That's our total time. To find this half of the fall, we're going to need to divide that by 2, which is 3.125 seconds. That's a pretty important step there. And then we'll square that. So really all we have to do now is multiply all these things together, and we'll take 0.5 times 10 times 3.125, and we should get for delta D 15.6, because we should have 3 sig figs here, 15.6 meters. You could calculate this using the first half. You certainly could. This is the easiest way to do it because we know VI at this point, and the height is the same either way. It should be the same even if we calculated it another way. For the last question here, we've got a penny falling from the observation deck of a tall skyscraper 370 meters. Tall. We want to determine the time required for the penny to free fall from the deck to the street below, and we're going to assume the penny does not reach terminal velocity. It probably would if air resistance would kind of balance it out, but we're going to assume that it does not. So we're going to, again, A is 10 meters per second squared, and it's falling, so VI equals 0. And we want to know the time here, so we are going to use the same equation we did on the last problem. Delta D equals VI delta T plus 1/2 A delta T squared. We know that it's 370 meters. We know that VI equals 0, so goodbye. We know 1/2 times 10 meters per second squared. And we don't know delta T. 1/2 times 10 is still 5 in my world, and I hope in yours. And if we divide that whole thing by 5, we should get 74 seconds squared equals delta T squared. And then we can square root that thing. Sorry about the movement there. And we will get delta T equals 8.6 seconds. There's your answer. It should be 8.6 seconds. We only have 2 sig figs there. So the time required for the penny to free fall from the deck to the street below would be 8.6 seconds. Seems like a long time, but it's also falling 370 meters, which is quite a ways. I hope this helps. We will check minus it on Monday.